All right, folks, a very warm welcome to today's session. This is our third session. Today is Thursday. It's our third session on an intuitive introduction to AI. So far, we have covered three topics. What is machine learning? Then we talked about correlation, causation, sequentiality, regression towards the mean, somewhat interrelated topics. That was our second theme. Last week we covered classification, classifiers, which is the ability for a machine to tell apart between a few different types. For example, to tell apart a cow from a duck, right? Or a sick patient from a not sick patient, or whether somebody is a loan, high risk for loan or not. So that's classification. We did a few metrics. I'll just quickly recap what we have done so far. In classification, as we said, our main goal is we send in an input, and then the machine determines which of the types that input refers to. For example, we may give the weight of an animal, and we may ask, given this weight, what do you predict this animal is? Do you identify it as a duck, or do you identify it as a cow? Likewise, we said that if you're talking about, let's say, grapes and strawberries, grapes are small in size and weight. The strawberries are a little bit bigger and heavier. So between them, there is a separating boundary. That boundary is called the decision boundary. So this is an example of binary classification. We said that if you can find the decision boundary in the feature space that separates the classes out well, then you are done. You have built a classifier. Today, guys, I'll apologize. I have a sore throat. I seem to have that every time I go for a walk down this part of the bay. Something is giving me strong allergies. So if I do cough, I apologize. All right. So today's topic is a different topic altogether. Unlike the previous weeks, where we talked about classification and regression, they belong to a class of algorithms that are called supervised learning. Why? Because you go through two phases. You first give the machine data to train it on. Then you validate you do some cross validations, but it's all a part of training. Once you believe you have built a good model based on the metrics, then you use it you can apply it to some test data, verify how well it is doing. All said and done, this is all part of the training ritual. You store the model somewhere and then you use it for production. When you use it for inference, you give it an input and output value comes out. On the other hand, it could be that input is a bunch of numbers, for example, for an animal. It could be the size or the weight and the color and whatnot, and you have to identify what is it. Or the input may be a picture of the animal. And from the picture, you have to tell what thing you are looking at. Or more practical uses are, for example, throughout most cities now, there are passive microphones embedded. Now, the idea is to have a rapid response whenever, for example, a gun is fired. Now, a car can misfire. Its exhaust may have a problem, in which case it sounds like a gun going off. And one of the achievements of machine learning is with pretty high accuracy, it can take the sound in and classify, was it a vehicle misfiring or was it genuinely a gunshot? If it is a gunshot, there has to be a rapid response from the person. So these are examples of classification. But today we'll deal with something entirely different, a new class of machine learning algorithms. These have to do with pattern recognition. Today and tomorrow are pattern recognition. So what do we mean by pattern? And why is it called machine learning? Why is it a part of machine learning? What is the machine learning? The answer to that is that suppose, or to enlighten you on the value of pattern recognition, imagine that you are traveling through San Francisco and you're walking down some street. You feel completely lost. So you look at the local map, you look at the local topology, you see some commercial you see some commercial buildings, then you move in some direction and you start seeing some residential buildings. You have to walk quite a bit to get a sense of direction. On the other hand, imagine that you're in a hot air balloon. If you're flying above the city, what would it do? In one glance, you will spot that the city is sort of segmented into zones. There is the commercial zone, the financial district. There is the park, the Golden Gate Park, with lots of greenery there. And beyond that, there are the residential homes. So, and you can tell that at the tip of the peninsula is the commercial district. Then you have the Golden Gate Park, and then you start seeing residentials after that. It's a very rough way of putting it. But now imagine that you have recognized that pattern in the data. And let's go back to our original situation. You are in the city again. What would happen? And you feel lost. You would have a much better bearing. Let's say you want to go to the Golden Gate Park. What would you do? You know that at the tip of the peninsula, in the north side, is the financial district. So all you need to do is sort of start heading south or southwest, and you'll hit the Golden Gate Park. So that's the value in pattern recognition. Knowing the pattern in data is a non-trivial task. There are many patterns you can recognize in data. The simplest pattern are called clusters. Whenever you have data, you will have clusters in it. And let me start writing what I'm saying. Is my screen shared?
Yes, it is.
Yes.
Running that. And so our next topic that we're going to do is pattern recognition. The value of pattern recognition is what was hard before. Once you see the pattern, sometimes it adds value and it becomes easy, as in the example of a lost tourist in San Francisco. So there are many aspects of pattern recognition. We'll focus on two aspects of clustering, which is for today. And tomorrow we'll talk about reduction. Pattern recognition is also very traditionally called unsupervised learning, though I'm not very fond of this term, supervised and unsupervised. I tend to avoid it. Unsupervised learning. In other words, there is no input and output. There is just data. You stare at the data, you make the machine stare at the data, and then say, all right, I see a pattern. Are we together with this? There's no input. So what does pattern mean? For example, suppose I give you, let's look at clustering. This is the topic for today. So what is clustering? It is also simple cluster detection or breaking up, identify all the clusters in the data. What do we mean by that? Suppose I have data like this, and imagine data shows up like this. Now, what do you see? If you look at it, you would say, well, I see three clusters, three groupings of the dots. These points are not just anywhere. Suppose I call this axis x1 and x2. They're not anywhere. They are localized in specific regions. Are we together? Now, the human eye is a marvelous learning engine. It detects clusters immediately, and we just take it for granted. It turns out that you cannot create a deterministic machine to detect your clusters. Like if you try, for example, if you go through your computer science program in the college, you must have remembered that you are taught searching and sorting. But you are not taught how to cluster data, find clusters in data. To find clusters in data is actually an at least an NP-hard problem. So the way you do it is you instead use machine learning as a probability, in a probabilistic manner, you find clusters. And using machine learning is very efficient. It does it in no time. So how do we do that? But before I address how we do that, I will explain to you why clustering is hard for machines to do. Clustering has a subjective element to it. One is that if you pay attention to, for example, this cluster, just pay attention to this cluster. What do you notice in this cluster? And let me just, for the sake of argument, and add a few more points. It will just illustrate what I'm trying to say. If you look at this cluster, what do you notice? That there may be subclusters. And so how many clusters there are in this data set depends upon what level of resolution you're searching clusters. You're searching the clusters at. So resolution matters. It's one of the reasons why it's not a deterministic problem. You have to tackle it with machine learning. But then you might say, now wait a minute, are you saying that something so utterly obvious to the human eye, one direct glance at this data, and you can spot the clusters, that it is very, very hard for a machine to do without using machine learning? And the answer, how do you explain that? And I will try to explain that sort of a mystery. See, if you look at the human eye, which does many marvelous things, but it has gone through humans, all mammals have eyes, all amphibians have eyes, keep going back in time, reptiles have eyes, sea creatures, the fishes in the ocean have eyes, the primordial sharks, all of them have eyes. So as far as we know, the eyes that you see in animals has gone through at least 100 million years of training from data, isn't it? If you treat it as a machine, it has gone through machine learning training for at least 100 million years. and through a billion living things it has learned.
Well-trained machine.
It's a well-trained machine. And is it a surprise that it recognizes patterns instantly? To contrast it with more recent faculties that have developed in human minds, for example, we say that the cognitive revolution, the ability for us to do very complicated reasoning using symbolic notation, is perhaps no more than 30,000 years old. That's what anthropologists say. 30,000 years of training is not much training compared to 100 million years of training. So you see that human beings make lots of errors in reasoning. We can be easily fooled by an argument, by a fallacious argument. We fall for it. If you remember, the first day, Monday, we started out with all sorts of fallacies. We confuse correlation with causation. We confuse sequentiality with causation. So just because I came to Silicon Valley in the late 90s, right, and there was a dot-com boom, surely I was the reason there was such a big economic boom and innovative boom in Silicon Valley, right? So that is a fallacious argument. And yet, while it looks ridiculous when I put it this way, we fall for it all the time. And we went through some real world examples, historical examples of that. So keep that in mind, that when we think about clustering, you actually have literally in your own self, in your eyes, a clustering algorithm that as of this moment, at least for 2-dimensional and 3-dimensional data, beats every known machine learning algorithm and solves the problem instantly. It gets more complicated in higher dimensions. It turns out we are not able to visualize data in 4 dimensions or beyond. In a past incarnation, for a few years, I used to be a physicist. And it took me a while to realize that what this physicist was saying in one of my graduate school courses is that the world is actually 4-dimensional. There are 3 dimensions of space and time, and actually they're quite entangled, right? And many things entangled. What looks like electricity to you, to another person moving, may look a bit like electricity and a bit like magnetism. So it was a very fascinating world. But one thing I realized, I tried very, very hard to somehow sit quietly and visualize in 4 dimensions. And I couldn't. So then comes all sorts of aids. You make diagrams, you project it down to 2 dimensions, to a page, right? And then you understand things. Then to make matters worse, came the string theorists, who started out first in 26 dimensions. Why 26 dimensions? Well, they're very serious reasons, but the joke was because English has 26 letters in the alphabet. Well, fortunately, with superstring...
Asif, could you repeat that? Didn't catch that one.
The original string theory had 26 dimensions. They insisted that the world is made up of 1-dimensional strings, the heterotic strings, which are vibrating in a 26-dimensional quantum space. And you ask them, why 26? There are very serious reasons for it. But the joke was, it's because English has 26 letters in the alphabet. Well, then came supersymmetry, and it brought it down to 10 plus 1 dimension. It's a pretty popular theory these days, superstrings. Sorry. The superstring theory. When people speak of string theory these days, they probably are meaning superstring theory. 10 plus 1 dimension is beyond our imagination. So what happens is that we reason and think in terms of equations, and it throws surprises at us. As many physicists have said, if anybody believes they understand quantum theory, they are completely misguided. It's impossible. It's impossible. So the reason I brought this thing out is to show to you that what comes through evolution, our instinctive abilities, our eyes, our pattern recognition, that helps us get a sense of the world. See, human beings, our eyes are a primary, in many ways, sense organ. We sense the world primarily through eyes. And if you have had a dog, you know that your dog senses the world primarily through the nose. Right? And many animals sense through the nose. But to our eyes, one of its remarkable properties is it recognizes patterns instantly. For example, if you're hiking in the forest, happily marveling at the beauty of the stream, the sky, and the trees, and all of a sudden you see in the bushes something that is striped and orange, you instantly know you're probably looking at a tiger. It doesn't take you reasoning. You don't have to reason that, oh no, now look at this. I think I see 4 legs and a tail. Oh, it also has stripes. Maybe it's a tiger and not a panther, not a cat, something else. You don't go through the reasoning. Instantly you recognize and you are in a flight mode. You're in a survival mode. So up to 3 dimensions, it works brilliantly. But data comes, unfortunately, in very, very high dimensional spaces. In fact, one of the most active areas of research these days in mathematics is the understanding of higher dimension spaces. It turns out that we really don't understand higher dimension spaces. We're completely befuddled by it. And one of the few tools that still makes heads and tails out of it, head and tail out of it, is actually machine learning, and in particular, the algorithms that we are going to talk about today. Clustering and the one we'll talk about tomorrow. So clustering is detecting clusters in data, in any dimensional data. It could be 100 dimensional, it could be 200. And are these numbers exaggerations, 100, 200 dimension space? Who looks at data in 100 dimensions? Well, it turns out most data exists in a few 100,000 dimensions. Right? Think of a picture. These days, people take very high resolution pictures, 42 megapixel. You realize that what it means, every single picture has 42 million dimensions sitting there, right? Likewise, when you look at text, when these machines do translations of languages, let's say English to French, so vice versa, they are looking at languages and embedding spaces quite often in 300,000 dimensions and sometimes million dimensions. And from there, they try to bring it down to a different space, a lower dimensional representation. But you start out with a very high dimensional representation, one hot encoding in a very high dimensional space. So higher dimensional spaces are the norm. And we'll learn about techniques to find clusters in this day, today, clusters in that. But that may raise the question, how do you know that there are clusters in data? It's okay, I can go I can go look for something and find it if it is there. But if it isn't there, it is not worth going and searching for it. For example, you wouldn't, in a normal frame of mind, walk into the woods searching for unicorns, simply because you will come back in vain. You wouldn't find any, except in mythologies. So the same question may be asked. How do we know if I'm given a random data set? There's a chicken and egg situation. If I find the clusters, I know they are clusters. But how do I know that there are clusters even before I go on the journey of finding it? Would any one of you like to venture a guess? So I will ask you a question. what proportion of data? Imagine data of all sorts: medical data, financial data, data from vibrational data coming from a machine, astrophysical data, right? Crime data, anthropological data, all of it, the wide variety of data that you find in our scientific world and the real world. What proportion of the data, roughly, do have clusters? Would they have clusters? Maybe 5%, maybe 10%, 5 or 10%. Anybody else would like to make a guess? Not one of my past students.
20%?
20% is a better guess.
I don't know.
Yes, it's better than 10. Anyone else, guys? Those of you who are there are lots of people here in the audience. Would anybody like to venture a guess between 0 and 100? What percentage of data would exhibit clustering?
Asif, if I
15.
can hazard a guess, the fact that the normal distribution and such things are much talked about, I would say about quite a lot of data is actually clustered.
I don't know if normal distribution is a compelling argument for clustering. You can go and build all the sandhills on the beach, but the beach is still one long continuity of sand.
But still, there are in nature there are okay. Once we see that, we know there is a pattern there. What I meant to say is that not every pattern is the same. The sand patterns are different than water patterns. The water patterns.
So I'll tell you what are not clusters. The molecules that make up the air that we are breathing are not clustered, isn't it? The molecules that make up the water that you drink are not
Correct.
in clusters.
They're not.
So I am now giving you very familiar and easy examples of non-clustered data. So then, now hazard a guess, what proportion of data in the world probably has clusters? Anyone? Guys, this is all about intuitive thinking. I've thrown out programming and I've thrown out mathematics from this introduction to machine learning. So think intuitively, think from practical experience. You have seen data, you have seen reality all around you. How often do you see clusters? Any more guesses, guys?
80%. How's that?
Percent. Pretty good, actually. So, any other guesses, guys? So now I'll tell you a fact that is sort of a very physicist thing, and that may give you a clue. When you stand on the overpass of a highway, imagine there's no congestion on the highway, and you are standing on the overpass. Theoretically, there's no all the cars should be evenly spaced out going by because it's free traffic, no congestion. But what do you see? Anybody has observed something? You see that cars, they go in waves. One bunch of cars will together move forward. There'll be gap, and then another bunch of cars will go forward. And you see bunching. And there's no reason. Like theoretically, the highway is wide open.
It's like the chaos.
Absolutely, yes. Another example is the emails or the message. Like I'm an old-fashioned person, so let me imagine emails coming to your mailbox. But you can bring it to the 21st century and think of messages on whatever people use these days, TikTok and iMessage and WhatsApp and Discord and whatnot. You notice that some days everybody seems to be wanting to reach you, and some other days you seem to be getting ignored, right? It seems that the world has conspired to what is the word that people do say these days in politics? Cancel you,
Ghost you.
ghost you, right? Or whatever the term is, social term is, right? And then the next day it changes again. But what you don't get is a very well balanced, steady stream of attention. So everywhere that you look up at the sky, the universe was created in a big bang. Matter got created. When you look up, let's say that the stars form, there is no reason. I mean, generally, if you look at the sky, you should have seen a uniform distribution of stars. And yet, what do you see when you look up? You see galaxies, which are clusters of stars. And if you wonder, where did the stars come from? They themselves are clusters of matter. Whereas, if you ask yourself, if the whole universe started out as a ginormous ball of light and space and time, how is it that all these globular clusters of matter are formed? How were the stars created? How did this intergalactic cloud not become one just uniform distribution throughout the universe? But they form. And then you can bring in gravitational theories and so forth. But the fact remains that if I have a rubber band completely uniformly stretched out, it doesn't spontaneously tear itself into little clusters. And yet you see clusters everywhere. In a movie that was a TV show actually that I like very much, but very old now, called Numbers. Anybody remember seeing Numbers? It's an old TV show. So and I'm mentioning it so that I can pin this fact to your memory. There are two brothers. One is a younger one, a bit of a genius, mathematical genius. The other is the FBI. So in criminology, they are taught that killers and criminals, they have a modus operandi. They have a pattern of behavior. You just have to discover the pattern and then be ready to pounce on them. At least you can identify who did it and how to catch that person. But apparently, at one point, there were a certain number of killings happening in Los Angeles, which showed no pattern at all. And the older brother, FBI, said, we can't use any of the things we have learned because this person is very smart. He has no patterns, right? And it's all over the place. The murders are all over the place. You don't see them here or there. And his younger brother, who was a mathematician, immediately said, the absence of pattern must be deliberate. You cannot have absence of patterns. You can't have absence of clusters unless you deliberately try to erase those patterns. So then he asked the question, what could cause, how could somebody erase their patterns? And then the rest of the story evolves and they find a pattern, a hidden pattern, which helps them catch the person. And so the lesson here that I'm trying to say is that, and this comes from chaos theory actually, nonlinear dynamics, the less fancy name for chaos theory. Chaos theory says that whenever there is any nonlinearity in the driving forces, then you're guaranteed to see things like this. You're guaranteed to see data that exhibits clusters and things. Most of the phenomena in real life, in the physical universe, in the financial universe, and every other thing, they show nonlinear dynamics, right? Nonlinear forces at work. And so clusters are everywhere. So I hope I've convinced you that it is worth looking for algorithms that do good clustering. Once that is established, now comes the question, all right, now that we know that clustering is worth doing, how do we do it? And as with any area of machine learning, it is replete with human ingenuity. There are practically countless clustering algorithms, very clever ways of clustering. And I'm going to introduce you to 3 ways of clustering. But the point is to show to you how different perspectives can approach the same problem and still solve it. And that's the beautiful thing about machine learning, that you can, and one of the things that I often say to people, one of the best ways that you can become good at machine learning is take real life and impose real life intuition onto the data. Tell yourself stories. If you notice, I did this course saying human beings respond to stories. And so I will tell you a lot of stories. So, believe it or not, to be a great data scientist, in my view, is to pick a story, something that will resonate with this data, and then use it as a guide to develop intuition into the data. So, for example, if I'm going to redraw this, and so, okay, let this data be there. Suppose you look at this data and you say, suppose this data, each of the data points in this space was a tiny little steel ball. A tiny little grain or nice round steel ball, which had some weight. Then, and let's say the data is, there's some data points here and there. Steel, metal, things have mass, isn't it? So when things have mass and you put a lot of those things together, you get a substance with density. Those areas feel dense. And dense is an intuition we have very clearly, isn't it? Right? So when you look at this picture that I have on the board, what can you tell about those clusters? They are regions that are dense, right? So for example, I could easily claim that this region, let me take it, okay. This region is dense, this region is dense, these are dense regions. And I can find the point of highest density. If I were to search for a point of highest density, it would be, I'm marking it in a color. Let's say that I look at all of this, maybe in this cluster, let me throw in some more points. All things considered, these 3 points, let's say. Would you agree? These are points that are very dense. So you say, all right, we will use density in the feature space. We'll pretend that no matter what dimensional space data comes in, we'll pretend as though it's real space like as in I can go left, I can go right, I can go up, down, I walk in this space. Just pretend that it is real space. And these points are not abstract data points, but they are tiny little steel balls. And so where the clusters exist would be hefty regions, would be dense regions, isn't it? Or in a way, let me put it this way, if I were to imagine, so think of this now and go with my intuition for a moment. Suppose I were to create a rubber band membrane, an elastic membrane, stretched out rubber membrane, and put these data points, lots of these data points in this thing, and these 3 clusters. If I were to put it on this membrane, what would it do to the membrane? It would create a depression, isn't it? At each of these places, I would start seeing a depression. I would start seeing a depression in the membrane, right? And that begins to give me an intuition. Even if let's say that I'm here, this big mass of points would have depressed this membrane enough that if I am a tiny little steel ball and really smooth, I will start drifting towards this valley, this depression. Does that make sense, guys?
So exactly like a space time.
Exactly. And so the intuition therefore is, if I want to detect clusters, what do? I start anywhere and I pretend as though each of these points are pulling me, right? They're attracting me. If they are attracting me, then I get, what am I? So suppose, let's look at this here. Suppose I'm at the point A. I will get attraction from this cluster. I will get some attraction from this cluster. Let me call it cluster 1, cluster 2, cluster 3. And I will get some attraction also from cluster 3. But which cluster will attract me most?
C1.
C1. Okay, is very near. And so the joint attraction of all of these clusters will basically take me on a trajectory that will quickly take me to the center of this cluster. Or rather, if you look at it in 3 dimensions, to this point, to the bottom of this valley, C1 clusters valley. Isn't it, guys? Does that make sense? Those of you, I would really appreciate those of you who are remote, if you could speak up and give some feedback, if this intuition makes sense. Anyone?
Yes.
Yes, it does, right?
Yes. This is similar to gradient descent, right? Or different thing?
It is quite literally gradient descent, though you call it not gradient descent actually. You call it gradient ascent, because if you imagine, and so for historical reasons, people have looked at it as a force hill. Like, where is the attraction maximum? Right? So if you look at the force of attraction, they usually will say literature, and this is completely equivalent. Here is another, and here is another hill. They make these hills like this and say, if I'm a point, I'm feeling the joint attraction from all of them, and I keep moving in the direction of greatest attraction, increasing attraction. That's historically as given, whereas I find it easier to think of myself as a very smooth steel ball, just sliding along in whichever direction the balls are pulling me and then falling into the right valley. Right? But the literature does think in terms of ascent. And so what happens is that the fastest way to go is to follow the direction of the force, the cumulative force, right? It so turns out that force that something exerts, the pulling force that something exerts, it's a bit of physics. People often call it's the gradient of the energy, gradient of the potential. And so people are looking for, it's a form of gradient ascent. You follow the gradient, direction of maximum gradient. The best way to do that is you look at the force and you say, okay, no, actually, let me just use force itself. See, the force is coming, you're here. There are different degrees of force that you're experiencing. You can follow the direction in which if you moved, you would get the higher force, right? Actually, the right technical term is higher potential, but I'll just use colloquially the word force. When you do that, force happens to be the gradient, but we won't get into it. You follow a process called gradient ascent of a function. Gradient, that's quite a mouthful, or hill climbing. But the way I look at it, it is gradient descent or falling into the valley. It doesn't matter. They both are equivalent ways of looking at it. Now, I won't get into the mathematics of it. Mathematics is dead obvious if you know calculus, right? And if you don't, actually, you don't lose anything so long as you get the intuition. So you notice that you can find clusters. Now, once you land in these areas, you find the 3 centers. Those centers, they have a fancy term. Those are called attractors, because they genuinely are, right? They're pulling you. These are attractors, these 3 centers are attractors. Once you have found the attractors, take the attractor around C1. All you need to do is find a certain radius within which density is at least reasonable amount, isn't it? You have a cutoff of density. You have some notion that this is a dense region. Anything lower than this I will consider to be not dense enough. And so you'll be able to draw some sort of a boundary around that attractor.
If I have to imagine like black holes, kind of like a given horizon.
Sort of, yeah. Yes. So you get that as one approach to finding clusters. This sort of approach, because they use the intuition of density, they are called density-based clustering. For those of you who want to pursue this a little bit more, just look into the scikit-learn library. It provides one implementation of density-based clustering in the class called dbscan. One particular implementation is, in fact, the oldest implementation of density-based clustering is dbscan. Very easy to use. If you know Python, you can quickly do it in a few minutes, but we won't go there. But then you say, all right, that is one way of looking at it. Are there other ways that you can look at it? There are two more ways. One of them is actually a very simple way. It says, no physics, we'll just do something pretty blindly. You know, these days we have election in the country, right? Upcoming presidential election. And there are these, I believe there are three major groups, right? The Republicans, the Democrats, and then there's an independent Kennedy as a candidate, right? So now I'll try to use a very topical notion to see if we can cluster. Imagine that there are people like this. And there are people like this. Let me just take two. Let me take two. What you do is, you don't know. Imagine that each cluster is like a party affiliation, right? A party that you're going to vote for. The point is, and each point is a person. And the whole question is, who is this person going to vote for? Right? Of course, the human eye will tell you it will vote for the left cluster. It belongs to the left cluster, and something else belongs to the right cluster. But suppose you didn't know. So what it says is that there's an algorithm called k-means. It is the simplest, but it has many variations. A k-means, k-median, accelerated k-means, and many k-means plus plus and whatever. As everything in computer science, the moment some good idea is discovered, there are 1,000 variants of that. So k-means is one of the oldest ones. It takes this very interesting argument, and you'll appreciate the beauty of this argument. It says just pick any 2 points, and declare them to belong to the 2 different parties. So suppose I pick A, and I pick, where should I pick B? Let's say I pick B here, randomly. Are we together? I pick 2 random points from the data set, and they happen to be A and B. If that is true, then do one thing. Connect them with a line. Take the perpendicular bisector of them. So here's the perpendicular bisector. I take this. Declare all points on this side of this line, right, to be. And the way you do that is, you basically ask, actually, you don't have to do this thing if this looks abstract. Actually, let me give you a simple interpretation. For each point, for every other point, actually don't do the perpendicular bisector, etc. It's a slight variation, and I don't want to use that. Take any point, like this green point, and ask, is it closer to A or B? It's closer to A. Then assign it to A's party, right? And so if you keep on doing it, you would agree that you will end up creating one affiliation of points that will be this, and another affiliation of point that will be this. You're done. So you picked any two random points, you call that they belong to opposite affiliations. They belong to two different clusters. And then each point you assign it to the point nearest to the nearest. Like every point you say, are you close to A? You belong to A. Are you close to B? You belong to B. Now, there's a word that you use for A and B. You call them centroids. Right? So first 2 points you randomly declare to be centroids. And then every other point you assign to either A centroid or B centroid.
So by selecting those two, A and B, should be far enough.
So we'll come to that. Yeah, I'm coming to it. Yeah. So guys, are we seeing this? I heard some question on the Zoom. A comment on the Zoom.
So Asif, if it happens, so essentially, will we replace the centroids if a newer, closer, or farther one comes up?
No. So let's go with this. So you have these two new centroids. What you do now is you take the center of the new clusters. So you created the green cluster and the orange cluster. Now find the center. And what is the new center? Somewhere here. And a new center somewhere here. Isn't it? Repeat this exercise and see if the points change loyalties. Are there any independent, undecided voters changing loyalties? You'll find that there are no undecided voters in this example, isn't it? Once you don't find any undecided voters changing loyalty, you're done. Well, you say, well, that was easy. That is so easy, but there's actually a bit of fly in the ointment because of the word random. Because what if happen chance, let me redraw this diagram. Luck doesn't favor you. You didn't pick good starting points. Suppose I do this. And suppose I pick 2 points. I will mark them as this point and this point. You see that I've marked those points pretty close to each other. Now you have a problem. What do we do? What will happen is, and this is where the perpendicular bisector thing, I'll bring it in. Just ignore the word perpendicular bisector. I don't want to use math. But what will happen is you can convince yourself that the way your clusters will form is these things will belong to green points. These points will all belong to orange, and this will all belong to orange. So you will end up finding 2 clusters which clearly are unsatisfactory. But all is not lost. Even if you happen chance you have terribly bad luck and you pick these 2 points, all is not lost. Because now, what did I say? Find the new centroids. So if you find the new centroids, you would agree that one centroid will form, I'll just call it C1, and the other centroid will be somewhere around here, C2. Convince yourself that these points, all the orange points, they probably have a center where I put C2. Does that make sense, guys?
Yep. Yes.
And now, once again, repeat the process. You make these things change loyalties. Now what will happen? look at all the orange points in the left cluster. Will they flip loyalties? Will this undecided voters change over to green vote? Which one are they closer to? Are they closer to C1 or C2?
C1.
C1. So they will immediately flip loyalty. They'll turn green. They'll join the Green Party. Right? And so what will happen is you will now end up with the same cluster. Let me just redraw it. And let me just mark those Initially, C1 was here, C1, and C2 was somewhere dangling in between, C2. But now what happens? These become all green. And these become all orange. And maybe
we recomputed the centroid after
yes, yes.
the
Then,
first round of affiliation was determined.
yeah, think about it this way.
Correct.
Any point here, what will it do? It will say, no, I'm closer to C1.
Right.
It will join the green cluster.
Exactly. No, makes sense.
That's what happens. And now you recompute the centroid of the new cluster, and this is your final result. You can convince yourself that it won't change from here now. This will become the new C1 prime. This will become the new C2 prime, right? And this is your final answer. So there will be a lot of reversals in votes, and perhaps there would be there would be a court challenge and some interesting drama. So, well, that's bringing this clustering down to a more common election metaphor. But this particular way is called k-means clustering. Sorry if you didn't like my joke offended anyone. I didn't mean to. But that's that. So k-means, the unusual thing about k-means is that it looks very simple and it's pretty robust. So it seems that why not just go with k-means? Now, here's the history of it. K-means clustering is perhaps the most widely used clustering algorithm. The great thing in its favor is its utter simplicity. It is so very simple, right? And widely used. There are a few problems with clustering and k-means. There are certain conditions in which it fails. There's pathological conditions, and I can tell you what they are. Suppose you happen to have data, let's say that there's perfect cluster here, perfect cluster here. And there just happens to be 2 points which are dead center. These 2 points that are marked, A and B. And let us say as a worst case situation, you end up picking those as your initial choices. Then what will happen is you will end up with a partitioning, a clustering that you'll never be able to get out of. What will happen is that you will end up with a cluster that is weird. This will be, why am I not able to? Oh, this. That will be one green cluster will be like this, and your red cluster, orange cluster will be like this. I'll just color the whole region. Now, if you look at it, these are not good clusters. Fortunately, there are certain mathematical measures that will warn you that, hey, your clustering may not be good. There are things like within cluster some squared distances. What it means is for every two points within the cluster, find the distance and square it, and then add it up, average it, or whatever it is. You will realize that because this point here and this point here, which are supposedly in the same cluster, are very far apart. Yeah, and you'll start seeing some distances. Like you're traveling, it's almost like you have to go to the other galaxy to meet the other point, which is supposed to be in your galaxy. Right? You're traveling way too far. How can you travel that far to meet the other guy? Right? So it gives you a clue that your clustering may not be right. And so in K-means, the recommendation is that you never do it once. It's a simple algorithm. You repeat it a few times. That's one. But then you may say, well, that's very easy to say. But when I'm clustering 1 billion points in a 100-dimensional space, I just burn through perhaps $10,000 worth of electricity or compute resources, 100,000. We can't do it again. So what do we do then? Yeah, there are certain tricks people use. None of these are reliable, by the way. What you do is you pick a point. So I said that when you have these clusters, happen chance you may pick points which are near each other. So one trick, which is not guaranteed to work, but in practice does work. You pick one point and pick the other point as far away from it as possible. So you will end up with this point. Now use these two as your starting points. And then do your clustering. And it sort of tends to work, though it's not guaranteed to work. And that explains why K-means clustering has many, many variants. People have tried over the years to come up with smarter and smarter ways. Now, it has a problem, though. There are multiple problems. One is, because you're computing distances, it becomes very, very expensive. I have 1 billion points. I have to compute the distance of 1 billion points to each of the two clusters. That is not good. For each step of this algorithm, I'll have to compute the distance of each of the billion points to C1 and C2. Right? So the way to solve that happens to exist. There are powerful mathematical structures called metric spaces and trees, metric trees. And one of the oldest example is KD tree, which say don't assign points one by one, but assign them bunch by bunch. Take a point and its neighborhood and assign it to C1 or C2, the whole of it. Right? So that accelerates it. You get better results. But there's another problem with K-means which you can't escape from. And that is the problem of...
So the bunching is after finding that
No, you'll have to put all the points into these bunches. You'll have to quantize it.
That is after selecting the two random points.
No. First, you just select you partition all the points into these regions,
okay,
these bunches or regions of the feature space. Then you pick two random points and assign entire region to one or the other.
Okay.
Right? So, very much like in politics, this whole region, we expect all of these guys are going to vote this way. Very much like that. Right?
So what's WSS means? The WSS, what that means?
Within clusters, some square distances.
So, what's the distance in a region you choose? You said people in this region. How big is that region?
Oh, that goes to the... See, I'll give you an intuition. Since you asked for it. See, suppose I have a lot of points. What you do is, there is a way of partitioning data.
If you trash.
Guys, please.
Everything will go into trash.
So guys, what this structure, so I'll just talk a little bit about it. What you do is you take this space, first pick an axis. Let's say that you pick the x-axis, right? Find the median point. Let's say that the median point is somewhere here. Divide it. go along the opposite one, do the same thing. This point is here. This point will be here. You see that, right? And then you have this point, and then soon you will realize that you'll have to divide it like this. You can keep on dividing, and soon you'll get little divisions. Sorry. Now, suppose I'll give you an example. Suppose you take 2 points as your starting point. Let us say, happen chance, you take this point A and this point, and I'll cheat a little bit, and just to illustrate the point. Obviously, I'm cheating here. Let's say that you pick another point, B. Yeah. You can convince yourself that this entire region you can assign to A in one go. Right? Yes. Likewise, this entire region, this region is A's region, it owns it. This region too will go to A. This gets tricky. This region will, let's say, go to B, isn't it? And this region, all of it will go to A. You saw how quickly you can do it. Right? So there are ways of accelerating it by pre-partitioning the data into regions, subregions. Okay? So this particular thing, I gave you a flavor of something called KD tree. Actually, I wasn't very precise. I made mistakes deliberately to keep the intuition there. And it belongs to a general class of algorithms called metric trees. Metric trees. Right? So we won't go there, but there are ways of making it faster. But now I'll tell you a fatal flaw with k-means clustering, out of which there's no getting out. And to illustrate the point, I usually bring up a particular data set. If you were to come and take a course on machine learning with me, I created a mischievous data set. Tell me, what do you see? I'll deliberately mark this data. And let's see if you can see something.
It's like I'm looking in the mirror.
Yes, exactly. You got that. This I call the smiley data set. It's actually there. It's one of those things. But it turns out that smiley data set completely wipes the smile out of most of the classical clustering algorithms. K-means clustering fails on its face, because there is no way you can apply k-means and get the 6 clusters that are there in this picture. It simply won't get it. It will fail. And there are mathematical reasons. I could use words like the clusters don't have a convex hull, and words like that. They are not convex, or they are not things like that. But let's not use mathematical terms. The basic thing is that the problem is the eyes seem to somehow be within the curve, contained within the eyebrows. Likewise, the nose somehow seems contained within the big smile, right? And in situations like this, and many such situations, k-means fails. There is another kind of clustering called agglomerative clustering. I'll briefly touch upon that. Which is a bottoms-up clustering. I will talk about it in a little bit. That also fails on its face. So k-means is easy, but it doesn't work. But you realize that if you use density-based arguments, it would work, isn't it? If you look at the 6 clusters, they are independently dense regions, right? And so you see a result that clustering, some algorithms work better than others. based on the data. If the data is simple, you don't want to do density-based clustering. It's expensive. K-means is fast and quick. But if the data happens to be like this, oh, then you're screwed. Then you have to use an algorithm like density-based clustering. And there are many, many algorithms. It turns out that no algorithm is perfect. You can always find cases that will break any algorithm for clustering. So clustering is actually a hard problem. And part of it is because of the resolution problem. There are clusters within clusters and so forth. So people have applied many, many techniques, spectral clustering using then graphs and whatnot to do it. Each of the clustering algorithms have their strength and their weakness. But the main message is no one algorithm will always work. That is also a corollary or a consequence of the so-called, and I will speak about that, a beautiful result in machine learning called the no free lunch theorem. There is actually a very serious result in machine learning that goes with the frivolous name no free lunch. So I'll give you a little bit of a history. This phrase no free lunch, we all know. We always know that there's always a catch to things, right? But its origin seems to be in Irish pubs. So some pubs, they decided that we need to increase traffic, and a good marketing strategy is to tell people that lunch is free. So it will attract people to the pub. You know, food is usually, if you have been to a pub, you realize that food is cheap, alcohol is expensive. So they don't mind giving you the food and then charge you for the alcohol. Except that they noticed that some freeloaders came, they would have the lunch and then they would just walk out. So then they made the rule, no free lunch. Only if you buy alcohol, you can get lunch free. So that historical phrase has stuck. Now, the way it's applicable in machine learning and AI is a very deep result. It says that you can't just learn one algorithm and say, I'm done for clustering or for anything, for regression, for classification, any of the things you learned. Because no one algorithm will always work or do better than other algorithms. Every data calls for some different algorithm that will be most effective. Right? And therefore, and here comes the result that's deep, the consequence of that. No one algorithm is more powerful than the other. So you cannot say, I remember over the decades, as I've been following this field, when decision trees came out, and it must be really ancient times, way back in the forks of ancient history, way back in the late 80s and 90s, when the decision tree came out, the commentators got carried away by the power of decision tree. And they said, by the way, the use of a decision tree like argument is agglomerative clustering. We'll come to that later. They said, decision tree wipes out all of machine learning is just decision tree. You can use it to do classification. You can use it to do regression with adaptation. You can also use it for clustering situations. So all that people need to learn is decision trees. They used to be called carts, classification and regression trees. Commercial implementations came out, great success. And people got really carried away. Just like today, people are carried away. They think a neural network can solve every problem. Or what is it? LLM can solve every problem, right? It is in every single decade that I have been in this field, I have seen experts confidently quantify that whatever algorithm happens to be fashionable at the time makes everything before it obsolete. I've literally been on radio shows where I've had people talk and say, with the coming of generative AI, all other machine learning algorithms are now rendered useless. These are meaningless statements. And I deliberately use this example of clustering to bring home the point because it's a simple example. But what is true for clustering is true universally, because the one thing about theorems in mathematics is that once proven, it is for all eternity. So let's put it this way. Pythagoras' theorem, which says what it says about hypotenuse and the sum of square of sides, has not been revised ever since it was created, isn't it? So it is not like Windows. Like Windows 11 or the latest version, they are still it's a half-baked product, still work in progress, or like any other software like Windows or database or whatever it is that you can think of. Products or theorems in mathematics, once proven, are true for all eternity. What you're looking at is a theorem. That theorem will forever be true. And so forever in machine learning, it will be true that there will never be the one algorithm to rule them all. Will never be. And I want you to, while you're still looking at it at an intuitive level, remember this most important rule. Never get carried away by the latest and greatest fashion. Learn this field well. Learn all aspects of this field. It is a very fascinating world of ideas. There's miraculous things that you're seeing all around you. Has deep roots in hundreds of years of mathematics, in physics, in computer science, in material science. And its crowning glory is that you cannot boil it down reductionally to one algorithm that will rule them all. Right? There will always be more and more interesting algorithms, and lots of them. And even the humblest algorithm, let's say for regression, it's linear regression. For classification, it may just be, or for example, it may just be the logistic regression. Or for clustering, it may be the k-means. There will always be situations where these algorithms will be the most effective and beat every more sophisticated algorithm. So that is the no free lunch theorem. So I was sort of looking and searching for a very simple example where I could drive home this deep point. And then I would like to finish by mentioning the last one, agglomerative clustering, just to show how completely differently people think. What agglomerative clustering says is that, see, do one thing. Take all the points. Suppose I have, let me just take these points. Take all of these points, and for what you do is find the two closest points, nearest points to each other. So find all pairwise distances. Perhaps the closest 2 points would be, I've made many points close to each other. Maybe these 2 points, right? So what you do is you write those 2 points down and replace them with the center of those 2 points, right? So let me call this A, let me call this B, and let me call this theta. You did that, right? Then go find another 2 points which are next closest to each other and replace them with another centroid point. And you keep on doing this process, right? Sometimes you may find 3 points which are equally distant to each other. That's perfectly all right. You can merge all 3 points together. Let me call this point pi, replace it with their center. Once you have done that, now what you do is, so you'll end up with lots of these little doubles, but sometimes triplets, sometimes 4. These things, treat them as though they are points that have replaced the original points. And now repeat the process. So you will start agglomerating points that are near each other, and you will end up with a beautiful structure. It will turn out actually that these two will meet and these two will meet at the top. And what you can see is that this form of clustering has one good quality to it, and I'll deliberately to exaggerate this, illustrate it with some point, is that you can say all the points are their self clusters, but then if you go from the top, you can cut here. Let me use a different color. I could cut at this line, this tree. This tree is called a dendrogram. I could cut at the green. So how many subtrees have I created? 2, isn't it? There is this subtree and there is this subtree. If you cut it at that point, this tree at that point, you have 2 clusters. Within each cluster, furthermore, now suppose you are looking for more clusters, I could instead cut it, let's say I cut it here. Now how many clusters do I see? I see 4 clusters. What it is saying is, as you zoom into the picture, you will naturally see more and more clusters. Are we together? If I were to cut it here, I would see 1, 2, 3, 4, 5, 6, 7 clusters. So based on what resolution you are zooming into, you will see different number of clusters. This is very popular in medical sciences to do that, because there the structures are complex. And sometimes you have to look at clusters at different degrees of resolution, right? So this is this people often call it, more common name of it is clustering, though agglomerative hierarchical clustering. Now what usually happens is people don't use such a big mouthful, agglomerative hierarchical clustering. They either use this word or they use this word. Agglomerative clustering or hierarchical clustering. Agglomeration, why? Because we are agglomerating the individual points into little clusters, subclusters, tiny clusters, and agglomerating up and agglomerating up. Agglomerating means sort of coalescing them up. So I will stop here. I taught you 3 clustering algorithms, and I also use this as a pretext to introduce you to the no free lunch theorem. Right? I hope that this has been fun, and we can go on and we can talk about many clustering algorithms. But today, the remarkable thing you notice is that there is no labeled variable. There is no training. The algorithm just goes at it, recognizes the cluster, comes back. So let us summarize what we learned. We learned that there is value in recognizing patterns in data. The simplest pattern that we focused on today is clustering. We made some compelling arguments that more often than not, data does exhibit clustering. Whenever there is nonlinearity of effect, you'll see clustering. Right? We went through 3 completely different point of views on how to approach clustering. One was a physicist argument, density, a little bit complicated with a little bit more fancy math, but it's a pretty reliable method. It uses the intuition of density and hill climbing or falling into the valley or whichever way you look at it, upside down. Then we looked at a very simple old way of looking at it, which is k-means clustering, very easy to work with, but with limitations. Some limitations can be removed, but actually some cannot be. And then we talked about agglomerative clustering. By the way, agglomerative hierarchical clustering also has the same problem. It doesn't work for the smiley dataset. Like the smiley picture, it will not work. Only density will work, and spectral clustering and a few other algorithms will work. But agglomerative will also fail. So the end message is there are many techniques to cluster. Which one will be most effective for a data set data reigns supreme. It pretty much guides you into picking the right algorithm. So don't, it is an unfortunate fact that most books on machine learning, they teach you only k-means clustering and maybe hierarchical clustering. Most of them, they don't mention density-based clustering. And they almost never mention any other clustering algorithm. But there are many fascinating, beautiful ways of looking at clustering, for taking different points of view about the data and then going about it from graphs, from this, from eigenvalue decomposition, many things people do, very smart things people have done. And at the end of it, the no free lunch theorem is there as a guidepost. It's worth learning many algorithms so that at least you know if one thing doesn't work, you know what to try. But if hammer is the only thing you have, there's no way you'll be able to cut cheese effectively. Go ahead.
So finally, what was the percentage of data?
Albert asked, so generally, what is the percentage of data in real world that actually admits reasonable clustering? The answer is greater than 99%.
Almost everything.
So the density-based algorithm is not being widely used because of it is called
computationally a bit intense. See, the implementation in scikit-learn, for example, is dbscan, which is a little unstable. The kind of algorithms that are stable, actually, you don't easily find implementations. I had to hand implement it. One of them is dentlu. Right. So if you ask how is Google, one of the most state-of-the-art clustering algorithms Google was using internally, it is dentlu, but there is no open source implementation available. Or there may be, but it's not very robust, not very popular. And also because it's computationally brutal, you don't want to implement it in Python. You want to implement it in Rust or C in a really high performance language because it is brutal.
Sorry, what algorithm is this one? I couldn't.
Yeah, I spoke of one more variant, one more density-based clustering algorithm called dentlu. D-E-N. Okay, I'll write it down. 1 second. Where's my pen gone? Oh, here it is.
Dentlu.
And there are many generations and variations of the dentlu algorithm. So if you were to come to my full course, obviously, you will get a much more rigorous and mathematically and programmatic implementations of these. But as we said, we are trying to keep to the idea, to the level of big ideas. So we'll end there. All right, folks. So this is all I had to say. I'll open it up to questions. I hope it was intuitive. I hope you learned something or you benefited from this. Any questions?
Asif, we talked about clustering. How is segmentation a marketing term, or is it the same as?
Yes, very much so. Marketing, more than marketing, your T-shirt sizes. How did they determine? Why have they chosen on smart, small, medium, large, extra large, extra large? How do they come up with those sizes? What they do is they look at people and they look at the body types and then they say, okay, I'm going to do this 5 sizes. Let's say 5 sizes: small, medium, large, extra large, extra large. Now you need to find 5 clusters in human upper body sizes, upper bodies. And the centroid of those, you make a shirt which is designed for the centroid of those body shapes. Quite literally. You do market segmentation. When you segment the market, segmenting a market is nothing but clustering. Right? And then you ask yourself, okay, if this cluster is there, what is the stereotype? Is the centroid? Like, who am I staring at? So it's heavily used in these areas.
That makes sense. The stereotype is the centroid, yes.
Yeah, without any supervision or any label, cluster is the only way to kind of go about it.
Cluster is the only way to go about
Because we don't know like what we are looking at. First recognize the pattern.
Yes.
That's the whole
Yeah.
intuition.
And you can rest assured that more times than not, very rarely you don't find clusters. Like I gave you examples.
Yeah.
If you look for clusters and air molecules in a room, you probably won't find it. Right? Or water molecules in a beaker. You
Maybe
probably
like
won't
we are
find
not
it.
going that, we don't have that level of tooling to
Yes,
sort of
to
like go
do that.
inside.
Yeah,
Right? Basically, if you are thinking about like a quantum mechanically, then you find the clustering there as well.
that's right. Actually, the trick there is the molecules themselves are clusters.
Yes, exactly, right? So because like if you think about like a quantum,
Yeah.
the wave function,
Yeah.
it's sort of like a cluster.
Yeah. No, see, the only reason I mentioned that is there are legitimate places where clusters may not exist traditionally, right? But they are relatively rare. And in fairness, I must say, I deliberately brought those counter examples to misguide you all first, so that you would have to think what number to pick. Otherwise, everybody would have said 100%.
Mhm. As if one more philosophical kind of question.
Yes.
If all the source code in the world is thrown into a clustering for clustering, the regular ones you'll be able to find out this is a for loop, this is an if loop, and those kinds of things. But would it be able to find? Technically, it should be like all the patterns that the Gamma book came up with, the iterator pattern, the visitor, you know what I mean?
Those patterns don't form clusters, to my knowledge. There's no recognition so far. Having said that, has programming language been clustered, like all the code been clustered? Certainly it has been. Yeah, you can look up the papers and the results of that. Even more, I mean, clusters are everywhere. Even if you look at the Git commits, right? There is an open source tool, a beautiful visualization that will give you a movie version of all the commits coming into your project. And it's hauntingly beautiful. And this non-linearity that I was speaking of, you literally see, it's almost like 4th of July fireworks. Suddenly, a lot of people are working hard and doing lots and lots of commits, and there's a firework in the sky in one area of the code base. Then other areas are quiet. Suddenly, another area lights up, becomes active, and then some other area is active. And you see these clusters of fireworks throughout your code base as in the activity on the code base. And it's beautiful to see, actually.
Yes, I think like it is like how zoom in you are going into the cluster and how zoom out you can go. So
Yes.
if you go zoom out in terms of like looking at the big picture, then you see the cluster.
That is true, yeah.
But
See,
you did say that it may or may not be able to find those kinds of clusters which are for the patterns, the Gamma book patterns.
see, I think you can, but so far nobody has reported that they have found it.
What was he?
He's talking about the classic design patterns in software, like as in the traditional design, the factory method, the singleton pattern, the decorator pattern, things like that. I haven't seen a paper or a report of such clusters found, but I don't see theoretically why they cannot be
Right.
at some level.
Got it. Thank you.
I hope I look forward to seeing you all tomorrow. If there are no more questions, I'll stop the recording. I apologize for my sore throat.
What are we talking about tomorrow?
Oh, the last is dimensionality reduction. Okay, guys, once again, if I may make a small spiel for support vectors before you guys leave, may I remind you that our courses for fall term, are about to start. We have a lot of very good courses coming up. These are substantially in-depth, both at theory level and a lot of practical real-world coding level. These are large language models, boot camps. Then there's an introduction to AI, which goes into all the neural network architectures. There's MLOps for those people who want to take their ideas to production. There are courses in AI agents. That's starting next week. So there are prompts, advanced prompt techniques, swag. So if it interests you, please look up the schedule and do register. And that ends my little advertisement.